Humanity has collectively discovered over 6,000 exoplanets, worlds, orbiting distant stars beyond our solar system. But this number represents only the tiniest fraction of what exists out there in the cosmic darkness. In our Milky Way galaxy alone, astronomers estimate there are more than 100 billion stars scattered across that enormous spiral of light and dust. Current research suggests that virtually every one of those stars hosts at least one planet, and often several more. When you consider that our galaxy is just one among trillions of galaxies spread throughout the observable universe, each filled with billions of their own stars and planetary systems, the numbers become almost incomprehensible. This staggering abundance of worlds means something quite remarkable. Any planet you can imagine, provided it doesn't violate the fundamental laws of physics, almost certainly exists somewhere in the vast expanse of space. Strange worlds with purple skies. Planets where gravity is so weak you could jump 50 feet into the air. Ocean worlds covered entirely in water thousands of miles deep. Desert planets baked under twin suns. Ice worlds where methane rains from toxic skies. All of these variations and countless others are out there, waiting in the darkness, circling stars we've never seen, in galaxies whose light hasn't even reached us yet. Given this extraordinary diversity of planetary environments, it raises a fascinating question that many people find uncomfortable to consider. Is Earth really the best possible world for human life? We've evolved here, certainly. Our bodies are perfectly adapted to Earth's gravity, its atmospheric composition, its day-night cycle, its climate patterns. But evolution doesn't optimize for perfection, it optimizes for survival. Just because we can live on Earth doesn't mean it represents the ideal conditions for human flourishing, longevity, happiness, or civilization building. What follows is a journey through 4 hypothetical planetary systems that would offer significant advantages over Earth for human habitation. These aren't fantasy worlds plucked from science fiction novels. Every system described here has been carefully constructed to obey the known laws of physics, orbital mechanics, and astrophysics. Computer simulations have confirmed their long-term stability. And given the sheer number of planets in the universe, worlds matching these descriptions almost certainly exist somewhere in the cosmos, orbiting unknown stars, awaiting discovery by future generations of astronomers with more powerful telescopes than we possess today. Our first destination might trigger a sense of recognition if you've ever watched a certain blockbuster science fiction film about blue aliens living in harmony with nature. This world represents a real-life version of Pandora, not a planet itself, but rather a habitable moon orbiting a massive gas giant planet. The moon is nearly Earth-sized, with a diameter of about 11,000 kilometers, giving it substantial mass and gravity. But this moon doesn't orbit its star directly. Instead, it circles a Jupiter-like gas giant, which itself orbits within the habitable zone of a Sun-like star. This configuration creates a gravitational environment somewhat different from Earth's. The combination of the moon's own mass and the additional gravitational influence of the nearby gas giant results in surface gravity, approximately 80% of what we experience here on Earth. For humans, this reduced gravity would have profound effects. Moving would require less effort. Lifting objects would be easier. Your joints would experience less stress over a lifetime. Athletes could achieve feats impossible on Earth. Higher jumps, longer throws, faster running speeds. The elderly and those with mobility issues would find movement significantly easier. Even your heart wouldn't need to work as hard to pump blood throughout your body. The gas giant parent planet resides comfortably within its star's habitable zone, that precious band of orbital distance where temperatures allow liquid water to exist on a world's surface. This positioning ensures the moon receives just the right amount of stellar radiation to maintain a temperate, life-friendly climate, not so close to the star that water boils away, not so distant that everything freezes solid. The conditions would support Earth-like weather patterns, liquid water oceans, precipitation cycles, and potentially lush ecosystems if life somehow arose there independently or was introduced by human colonists. Like our own moon is to Earth, this habitable moon would be tidally locked to its gas giant parent. Tidal locking is a natural consequence of gravitational forces acting over millions of years. It means the moon's rotation period exactly matches its orbital period around the gas giant. Consequently, One hemisphere of the moon perpetually faces the gas giant, while the opposite hemisphere never sees it at all. For anyone standing on the near side, the side facing the planet, the gas giant would be permanently fixed in the sky, never rising or setting, an eternal celestial companion dominating the heavens. Imagine that view for a moment. A colossal planet, perhaps 10 times Earth's diameter, hanging motionless in your sky. You could watch weather systems the size of entire Earth swirl across its cloud bands, lightning storms crackling through its atmosphere, its numerous other moons transiting across its face like moving dots. From the surface of our habitable moon, this gas giant would appear roughly 20 to 30 times larger in the sky than our moon appears from Earth. During the day, it would be visible as a massive disk showing intricate cloud patterns and perhaps a prominent ring system catching the sunlight. At night, it would glow with reflected starlight, a cosmic lighthouse illuminating the darkness. This view alone might justify calling this world superior to Earth for human habitation. The psychological and cultural impact would be immense. Every human on the near side would grow up with this enormous planet as a constant presence in their lives. It would feature in their art, their religions, their philosophies, their sense of place in the universe. It would serve as an ever-present reminder that their world is part of something larger, orbiting not just a star, but another planet, nested within a cosmic dance of gravitational forces. But the benefits of this configuration extend far beyond aesthetics and psychology. The tidal locking of the moon to the gas giant would stabilize the moon's axial tilt over millions or even billions of years. On Earth, our axial tilt, the angle at which our planet's axis points relative to our orbital plane, wobbles slightly over tens of thousands of years due to gravitational perturbations from Jupiter and other planets. These wobbles contribute to ice age cycles and long-term climate variations. Our relatively stable axial tilt of about 23 degrees is actually maintained by our unusually large moon, which acts as a stabilizing influence. On our hypothetical moon, the massive gravitational presence of the nearby gas giant would lock the moon's orientation even more rigidly than Earth's moon stabilizes our tilt. This would prevent the extreme axial tilt variations that could otherwise occur over geological timescales. Without such stabilization, a world might wobble dramatically, causing its poles to sometimes point almost directly at its star. This would create devastating seasonal extremes, summers of endless daylight and scorching heat, alternating with winters of perpetual darkness and bone-chilling cold, with entire hemispheres becoming periodically uninhabitable. Our Pandora moon would avoid these extremes. Its climate zones would remain consistent over millions of years. The tropics would stay tropical. The temperate zones would stay temperate. The polar regions would stay cold. This climatic stability would be invaluable for the development and persistence of complex ecosystems and for human civilization building. You could establish cities in locations confident they wouldn't become uninhabitable due to long-term climate shifts caused by axial wobble. Additionally, the gravitational interaction between the moon and the gas giant would generate tidal heating within the moon's interior. Tidal heating occurs when gravitational forces stretch and compress a body, converting mechanical energy into heat through internal friction. Jupiter's moon Io experiences extreme tidal heating, making it the most volcanically active body in our solar system. Europa and Enceladus experience moderate tidal heating, which maintains liquid water oceans beneath their icy surfaces, despite being far from the sunday. Our habitable moon would experience a carefully balanced level of tidal heating, enough to provide benefits, but not so much as to cause destructive volcanic activity. This internal heat would supplement the moon's residual heat from its formation and the heat generated by radioactive decay of elements in its core. The additional energy would help maintain geological activity, driving plate tectonics, volcanic activity, and mountain building processes. This might sound dangerous, but moderate geological activity is actually beneficial for long-term habitability. Plate tectonics recycle carbon dioxide and other chemicals between the surface and interior, regulating atmospheric composition and helping maintain stable temperatures through the carbonate-silicate cycle. Volcanic activity releases gases that replenish the atmosphere and create nutrient-rich soils. The tidal heating would help prevent the moon's interior from cooling and solidifying, which would shut down these processes and might eventually lead to a dead, Mars-like world. The tidal heating might also help prevent the kind of massive supereruptions that have periodically devastated life on Earth. When a planet's interior generates too much heat without sufficient release mechanisms, Magma can accumulate in enormous chambers beneath the surface until pressure builds to catastrophic levels. The result is a supervolcano eruption that can inject so much ash and sulfur dioxide into the atmosphere that global temperatures plunge, causing mass extinctions. The steady release of internal heat through moderate volcanic activity and tidal heating might prevent such dangerous accumulations of magma. Similarly, the geological activity maintained by tidal heating would help prevent the kind of runaway ice ages that can occur when a planet's carbon cycle shuts down. Without active volcanism releasing carbon dioxide into the atmosphere, ice ages can spiral out of control as expanding ice sheets reflect more sunlight, cooling the planet further, causing more ice formation in a vicious cycle that can eventually freeze an entire world solid. The geological activity on our tidal moon would help maintain the delicate balance of greenhouse gases needed for stable temperatures. The orbital mechanics of this system would create a day-night cycle quite unlike Earth's. The moon would take approximately 10 Earth days to complete one full orbit around its gas giant. Because the moon is tidally locked to the planet, a complete day-night cycle on the moon's surface would also last these same 10 days. For someone standing on the moon's surface, the sun would slowly rise, arc across the sky over a period of about 5 days, then set, followed by 5 days of darkness before the cycle repeated. This extended day-night cycle would have profound implications for any life on the surface. And for human colonists, 5 continuous days of sunlight would allow extensive photosynthesis, potentially leading to enormous plant growth. But 5 days of darkness would be challenging for plants and animals adapted to Earth's 24-hour cycle. Life would need to adapt with strategies for storing energy during the long day and surviving the long night. Animals might become primarily diurnal or nocturnal, depending on which period they're active. Plants might develop large energy storage organs to survive 5 days without photosynthesis. For human colonists, the extended cycle would require significant adjustments to sleep schedules, work patterns, and agriculture. You couldn't grow traditional Earth crops on a 10-day cycle without artificial lighting. Indoor farming with controlled lighting would likely become essential. People's circadian rhythms would need to adjust, or they'd need to live in habitats with artificial day-night cycles matching human biology. But here's where the orbital configuration creates something truly magical for inhabitants of the near side, the hemisphere facing the gas giant. During the 5-day night period, the surface wouldn't be plunged into complete darkness like Earth's nights. Instead, the massive gas giant hanging overhead would reflect sunlight down onto the moon's surface. The gas giant would go through phases similar to our moon's phases, but reversed. When the sun is behind the moon from the perspective of someone on the surface, what would be the moon's midnight, the gas giant would be fully illuminated, appearing as a brilliant full disk in the sky. The amount of light reflected from this full gas giant would be extraordinary. Our moon reflects only about 12% of the sunlight that hits it, and even a full moon provides roughly 1/400,000th the illumination of the Sunday. But a gas giant 10 times Earth's diameter would have about 100 times the surface area of our moon as seen from Earth. And many gas giants have highly reflective cloud tops that bounce back 40 to 60% of incoming light. The combination of greater size and higher reflectivity would mean this gas giant could reflect perhaps 10,000 times more light than our full moon during the moon's nighttime. This would transform nighttime on the near side into something resembling perpetual twilight. You could read a book outdoors by giant light without artificial illumination. Shadows would be clearly visible, though softer than daylight shadows. The landscape would be bathed in a steady, ghostly glow, bright enough for human eyes to see colors rather than the black and white vision that dominates during Earth's nights. Wildlife would be active during these illuminated nights. Plants might even conduct some limited photosynthesis, depending on their sensitivity thresholds. For the inhabitants of the far side, the hemisphere that never sees the gas giant life would be more Earth-like. They would experience traditional nights of darkness when the sun set, seeing only stars and perhaps smaller moons of the gas giant system. The cultural differences between nearsiders and farsiders would likely be pronounced. Nearsiders would grow up never knowing true darkness, never seeing stars, except during the rare circumstances we'll discuss momentarily. Farsiders would experience normal day-night cycles, see the stars regularly, but never witness the spectacular gas giant hanging in the sky. The border region between near and far sides would be especially interesting. The gas giant would appear on the horizon, partially visible, creating a zone where the giant rises and sets due to the moon's slight wobbling motion called libration. These border regions might become prime real estate, offering occasional views of the gas giant without the perpetual brightness that prevents stargazing. Now we arrive at what might be the most spectacular feature of living on this moon. During each 10-day orbital cycle, if the orbital geometry aligns properly, the moon will pass directly between its star and the gas giant, causing a solar eclipse as seen from the moon's surface. But this wouldn't be like the brief solar eclipses we experience on Earth, where the moon's shadow races across the surface for just a few minutes. Instead, as the moon moves through the gas giant's shadow, an enormous shadow would sweep across the entire near side, lasting potentially several hours. During these eclipse events, the perpetually bright sky would darken dramatically. The temperature would drop noticeably as the sun's warmth was blocked. The stars would emerge in the sky for the first time, filling the heavens with thousands of visible points of light. For nearsiders who live their entire lives under either sunlight or giant light, this brief window of true darkness would be a sacred, magical time. The emergence of stars during these midday eclipses would likely hold profound religious and cultural significance. Imagine being a child growing up on the near side, hearing stories about the stars that supposedly fill the universe, but never seeing them because the giant in your sky is always too bright during the night. Then, on certain special days that occur like clockwork, the sun disappears behind the giant, darkness sweeps across the land, and suddenly the entire cosmos reveals itself. Thousands of stars appear. The cloudy band of the galaxy stretches overhead, and you finally understand viscerally that you live in a vast universe rather than just under a sun and a giant. These eclipse moments would be transformative experiences, festivals of darkness, times of revelation and wonder. The orbital dynamics could create different types of eclipses. Total eclipses when the moon passes directly through the center of the giant's shadow. Partial eclipses when only part of the sun is blocked. And depending on the orbits of other moons in this system, you might occasionally witness spectacular triple or quadruple eclipses as multiple bodies align, creating complex shadow patterns on the surface. From a scientific perspective, these regular eclipses would provide extraordinary opportunities for astronomy and atmospheric studies. During eclipses, scientists could observe the sun's corona, study the gas giant's atmosphere as sunlight passes through it, creating a ring of light around the planet's silhouette, and conduct observations of distant stars and galaxies without light pollution. The predictable schedule of eclipses would allow for planned research campaigns, turning these events into regular scientific opportunities rather than rare chance occurrences. We should also consider some practical advantages and challenges of this world. The reduced gravity would have mixed effects on human health. On the positive side, reduced joint stress and easier movement would benefit quality of life, especially for older individuals. Construction projects would be easier with lighter materials. Transportation would require less energy. However, reduced gravity can cause bone density loss and muscle atrophy over long periods, as astronauts experience in microgravity. Colonists would need regular exercise regimens and possibly gravity simulation devices to maintain physical health. The 10-day cycle would require completely rethinking agriculture, sleep patterns, and work schedules. Greenhouses with artificial lighting would become essential infrastructure. Cities might operate on staggered schedules to maintain 24-hour activity cycles despite the unusual day length. Or perhaps human culture would adapt entirely, with people remaining active for much longer periods and sleeping in extended blocks. The presence of the giant would also create unique navigational advantages. On the near side, the giant's position in the sky would be fixed, providing a permanent reference point for navigation and timekeeping. Mariners crossing oceans would always know their longitude relative to the subgiant point, the location directly beneath the giant. The giant's cloud patterns would change over time, providing visual markers for tracking the passage of days and seasons. This world would likely be part of a larger moon system, with multiple other moons orbiting the same gas giant. Some might be small, rocky bodies, like our moon. Others could be large ice moons like Europa or Enceladus. Depending on their orbits, these sibling moons would regularly transit across the giant's face, as seen from our habitable moon's surface, appearing as dark dots moving across the bright disk. If any of these other moons were also large enough and positioned well enough to be colonized, a multi-moon civilization could emerge, with populations spread across several bodies in the same system, all orbiting their parent giant together. The resources of such a system would be extraordinary. Gas giants typically have extensive moon systems with diverse compositions, rocky inner moons rich in metals and silicates, middle moons with mixtures of rock and ice, outer moons dominated by water, ice, and frozen volatiles. A civilization with the technology to travel between these moons would have access to every element and compound needed for industry. The gas giant itself would have a powerful magnetosphere, trapping charged particles, creating radiation belts that could be hazardous, but also might provide unique energy harvesting opportunities. From a long-term perspective, this moon offers stability. The gas giant's gravitational dominance in its region of space would help protect the inner moons from asteroid impacts by either capturing or deflecting incoming objects. The complex gravitational interactions within the moon system would clear debris from stable orbits over millions of years. While impacts would still occur, the rate might be lower than on Earth, reducing one category of existential risk. The star at the center of this system would need to be carefully chosen for long-term habitability. A star too massive would burn through its fuel quickly, leaving insufficient time for complex life to evolve or for human civilization to establish itself across the system. A star too small might provide too little energy, forcing the habitable zone inward to distances where tidal effects become problematic. An ideal candidate would be a G-type star like our Sun, or perhaps a K-type orange dwarf that burns more slowly and steadily, providing a stable habitable zone for tens of billions of years, far longer than the Sun's remaining lifetime. This Pandora moon represents a genuinely viable alternative to Earth, offering reduced gravity, spectacular views, enhanced geological activity for long-term habitability, and the intangible but profound psychological benefits of growing up under an alien sky with a giant planet overhead. The challenges are real. The unusual day-night cycle, the perpetual brightness preventing stargazing on the near side, the complexities of building a civilization in reduced gravity, but none are insurmountable. Given the billions of gas giants that must exist in the cosmos within habitable zones, statistical likelihood suggests that worlds matching this description exist, waiting in the darkness for humanity's descendants to find them. Now we leave our moon orbiting a gas giant and travel to our second destination, a world that at first glance appears almost indistinguishable from Earth. A warm, yellow star shines in the sky, providing comfortable temperatures and familiar illumination. The planet itself matches Earth in size, mass, and composition. Oceans cover the surface, continents rise above the waters, an oxygen-rich atmosphere supports life. Everything appears perfectly normal until you look more carefully at the star in the sky. With optical instruments, perhaps even with the naked eye under the right conditions, you would notice something impossible, something that violates every intuition about how stars behave. The light from the star bends strangely near its edge, and if you watched carefully, you might catch brief moments when the star appears to develop a ring around it, a halo of distorted light. That's because this isn't just a star. Welcome to the Black Sun planet, a world orbiting a binary system consisting of a normal star and a stellar mass black hole locked in an eternal gravitational embrace. The star component of this binary is similar to our Sun in mass and temperature, a yellow G-type main sequence star producing steady light and heat. But orbiting this star, bound by mutual gravity, is an object far more exotic, a black hole with a mass 10 times that of the Sunday. These two objects don't orbit a point between them. Instead, because the black hole is so much more massive than the star orbits the black hole, dancing around it in a tight embrace, held in position by gravitational forces that would tear lesser bodies apart. The physics of this binary system creates a mesmerizing orbital dance. The star traces a path around the common center of mass, which lies well inside the black hole given its 10-to-1 mass advantage. From a distant vantage point, you would see the star orbiting what appears to be empty space, pulled by an invisible companion. But the companion isn't truly invisible. The black hole's gravity is so intense that it warps the very fabric of space-time around it, bending light from background stars and sometimes from the companion star itself, creating telltale distortions that reveal its presence. Our Earth-like planet orbits this entire binary system, bound gravitationally to both objects together. The orbital mechanics are complex but stable when properly configured. The planet must orbit at a specific distance, where the combined gravitational pull of both the star and black hole provides exactly the centripetal force needed to maintain a circular orbit. Because the total mass of the system is 11 times our Sun's mass, 1 solar mass in the star plus 10 in the black hole gravity is much stronger, and objects must orbit faster at any given distance to avoid falling inward. At a distance equivalent to Earth's distance from our Sun, about 150 million kilometers, one astronomical unit the planet would need to orbit much faster around this massive binary than Earth orbits the Sun. A complete year on this world lasts only about 110 Earth days. The seasons would cycle more than 3 times faster than Earth seasons. Spring, summer, autumn, and winter would each last less than a month. The faster orbital speed means more intense seasonal changes as the planet rapidly changes its position relative to its star. The black hole itself would be tiny compared to the star. Despite containing 10 times the star's mass, the black hole's event horizon, the boundary beyond which nothing can escape, would be only about 60 kilometers in diameter. That's minuscule compared to the star's diameter of about 1.4 million kilometers. If you could somehow see both objects side by side, the star would appear nearly 23,000 times wider than the black hole. Yet gravitationally, the black hole completely dominates the system. Its immense mass concentrated into an impossibly small volume. From the surface of the planet, during normal conditions, the star would look and behave just like the Sun in Earth's sky. It would rise, arc across the sky, and set, providing light and warmth. The black hole, despite being more massive and gravitationally dominant, would be invisible to the naked eye, just a point in space with no light of its own. You could live your entire life on this planet without directly observing the black hole, knowing of its existence only through indirect evidence. However, with advanced telescopes and careful observation, particularly during specific orbital configurations, you would witness something extraordinary. When the star passes directly behind the black hole, as seen from the planet, gravitational lensing would become visible. The black hole's gravity would bend light from the star, warping its appearance. The star's light would follow curved paths around the black hole, creating an Einstein ring, a complete circle of light surrounding the black hole's silhouette.